Alright, in this video we're going to talk about the period of a pendulum and the period of a mass oscillating on a spring. And to look at this, we're going to use PhET simulations, and this will be part of your lab as well. So you probably have already used a PhET simulation at this point in one of your classes, but if not, if you Google PhET, so P-H-E-T, it'll pop up, and all these simulations are made by the University of Colorado, and there's simulations for all sorts of different subjects, all the sciences, and some math. So we are going to look at the masses in spring simulation and also the pendulum simulation. So if I click on masses and springs and run, you can see that over here I've got 3 different springs. I have a ruler that I can move around. I've got some masses where I know their actual mass and some that I don't. And then over here I can adjust different things. So I can change the softness of the spring, which is the spring constant for the 3rd spring. I can turn friction off or way down, or I can make it really large. I can have it show like gravitational potential energy, elastic potential energy, thermal energy in the case of frictionless or with friction springs. I can slow down the time a little bit so it's easier to observe, and I can also change the gravity and what planet I am on, right? There's also a stopwatch where you can use to actually time an oscillation and figure out how long it takes to go down and up. So masses and springs are an example of simple harmonic motion, because if I were to take a mass and place it onto a spring, and I were to stretch it down, right, and release, it would oscillate back and forth indefinitely. If there was no friction, it would just go on forever and ever. So simple harmonic motion is when something repeats its path. So that's why circles are an example of simple harmonic motion. This sort of oscillation, waves, and then we'll see also pendulums, right? So there are 2 different things that affect how long it takes for a spring to oscillate once. And so that's the period, right? So let me go to the Elmo. And this may be kind of intuitive to you, and I'm not going to derive this equation, I'm just going to give it to you so you can use it and observe. But for most cases, and I'll say that there are some instances where we have numbers that fall outside of this, but in general, we can use this equation, that t, which is the period in seconds, right, or the time to complete one oscillation of a mass on a spring, is equivalent to 2 pi times the square root of the mass that's hanging from the spring over the spring constant. So meaning that the bigger the mass is, the bigger the period. So that kind of makes sense. If you think you've got a big heavy mass, it's going to oscillate further given if k stays the same, so it's going to take a longer amount of time. And then your spring constant, depending on how soft your spring is going to determine how quickly it's going to, or what the strength of the force is for it to return to its original position. So if you have a really big spring constant, then it's going to be a pretty strong spring, and therefore the period is going to be very small. Whereas if it's a very small spring constant, then it will stretch out like a slinky and take a long time to go back and forth. So this is how we calculate the period of an oscillating mass on a spring. So let's go ahead, and I want to look at another simulation now and look at the idea of a pendulum. So let me open up that. And the pendulum equation looks pretty similar. So if I run this, we'll see that there's a lot of different variables and things that I can adjust. Oh, it's not going. Let me see. Let me click it again. Alright, so over here we have the mass on the end of the pendulum. We also we can affect the length of the pendulum arm. Right? We can change whether or not there's friction. I can slow down time so I can see it better, and I can affect gravity, and again I can time things, and I can show the energy and whatnot. So if I were to bring this up to a specific angle, and again it will the angle will show there as well, and we'll see how angle actually affects the period, right? And so if I were to release it, it would swing back and forth. And if I wanted to use my photo gate timer, what this will actually do is it will measure just one oscillation. So I'll hit start, and you notice the time doesn't go until it passes through its original position, and then it will time the actual period that it takes the pendulum to oscillate once. All right. So if we look at the equation for a period of a pendulum, so there's two different variables that affect it. And again, we'll see that this equation really isn't complete, but for most cases will work. And we can see sort of what other variable might affect the problem as you work through the lab. So the period of the pendulum, or the time for it to swing once, is equal to 2 pi the square root of L over G, where L is the length of the arm of the pendulum. So if you have a very big, long arm, it's going to take a longer time to go back and forth. It's going to swing really far this way. Whereas if you had a little short arm, it would just swing back and forth really quick. And then the other variable is gravity. So the gravitational pull and the acceleration due to gravity is going to affect how fast the pendulum essentially falls, and therefore the time that it takes for it to oscillate once. So if you have a very large number for gravity here, you end up having a very small period. So it's going to accelerate faster, so it's going to be swinging faster. Whereas gravity is very small, then it's going to take a longer time for it to fall and swoop through its path. Right? So these are the two equations that you need to complete the lab and the classwork on period of a pendulum and period of a mass on a spring.